Hi, welcome to ERC Technology, and in this video I will be showing you how to create a BJT amplifier, and then we will be measuring the gain. First, let's put the title here like this is the gain at different loads of a basic emitter, common emitter amplifier. Gain, different loads of a basic common emitter amplifier. Then we click on the transistor and select one NPN transistor. And then we click on the resistor. We will put four resistors in this circuit. Let's rotate our resistor so that it will be vertical. And we will be putting the values of these resistors, namely for the first one, R1, let's make it 68 kilo ohms. For the second one, let's make it 47 kilo ohms. For the third one, let's make it 10 kilo ohms. And for R4, let's make it 4.7 kilo ohms. Then after that, we connect together the R1 and the R2. Same with R1 and R3. Let's just move it a little to the left so that they will be aligned. R2 and R4 will be connected together. And the NPN transistor, the collector of the NPN transistor will be connected to R3 or R2. The base will be connected to the in between R1 and R3. And then for R3, we will connect it down here to R4. And then the emitter will be connected to R4. I'm sorry, I need to cancel this wire because the collector is connected to the R2, the emitter connected to R4, and the base connected in between R1 and R3. And then we will be having here a voltage source, a DC voltage source at the top, and we have to rotate it so that the positive side of the DC voltage source will be connected here, and of course the negative side will be connected to a ground. Then this will be used as our biasing voltage source for our amplifier. Let me just fix this for a while. Okay. And the voltage source DC must be 12 volts. And there you go. You have your amplifier, BJT amplifier, NPN. And of course, we have to put our input source, which will represent the AC voltage here. And this input voltage will be connected to a capacitor. So let's put a capacitor here before the base and another capacitor uh, on the collector side. The value of these capacitors C1 and C2, we will make it 10 microfarad each. So this will be 10 microfarad. And we need another capacitor which will later be connected on the resistor R4, which is connected on the emitter. and this capacitor will be having a value of 100 microfarad. Now we will just make this ready because in this example, I will first measure the gain without using C3, or shall we call it CE, because it's connected to the emitter of the transistor. Now the capacitor C2, which is connected to the collector, will be here, and the capacitor C1 will be connected to the base of the transistor. And then the other side of the capacitor will be connected to the voltage source AC here, which will be representing the input voltage. And then in the output side, we will be placing a potentiometer or the variable resistor, and we will just connect one side of it because the examples that we will do will be varying the value of the potentiometer, and in the beginning there will be no load or no potentiometer will be connected. So the input voltage we will be in the input voltage we will be using a peak voltage value of 0.2, 0.4 peak voltage. For example, let's use zero point 0.4 volts as our VP input, and the that is the peak voltage input. And then we will be placing here a voltmeter, and this voltmeter we will make it periodic for the interactive simulation so that we will see the peak to peak voltage as well as the RMS voltage. And of course, we will name it as V input. Instead of probe 1, we will put V in. And then on the right hand side of the circuit, we will make another voltmeter here, which is named as V out. And we will also need to click the periodic here, interactive simulation, so that the VPP and the VRMS will be both displayed. There you go. Let's double check it. So our input voltage will be zero point 0.4 volts at a frequency of 1 kilohertz. Our output voltage will be measured without the load resistor. That's why I did not connect it here. So in the beginning, we will have no load. And our voltage here, we will call this as VCC. This will be equal to 12 volts. Can cancel the V here. That's 12 volts. And we have R1 68 kilo ohms, R2 47 kilo ohms, R3 10 kilo ohms, R4 4.7 kilo ohms, and then our NPN BJT transistor here. The collector is connected to the capacitor C2, which is 10 microfarad. The base of the transistor is connected to 10 microfarad capacitor 2 here. And then we have weighting CE or emitter capacitor, which will be not connected across R4 for the meantime. And we have a potentiometer or potentiometer, which is having a value of 10 kilo ohm right now, but 10 kilo ohms, but we will not be using it for the meantime because the first thing we will do is not to connect the load resistor. And then in the input side, as you can see here, we have AC. So we are expecting that the value of the output voltage will be much bigger than the input voltage of zero point 0.4 volts. So let's try it. Let's run the simulation. And as you can see here, the peak to peak voltage is around 1.2671 millivolts. And in the output side, we have a peak to peak voltage of 23.907 microvolts. So there's something wrong with the circuit. So we have to stop this. I think we did not put the ground. So let's put the ground here at the bottom. So let's try it again. Let's run the simulation. And there you go. You see here that the peak to peak voltage is around 800 volt or 800 millivolt or zero point 0.8 volts, which is the equivalent of 798.79 millivolts. So this is around zero point 0.8 volts peak to peak input voltage. And in the output here, we have a peak to peak voltage output of 6.8699 volts. As you can see, approximately it's 7 volts in comparison with the 0.798 or zero point 0.8 volts, which is less than 1 volt. The input becomes very large in the output side. It becomes 6.8 volts. So there you go. This means that the amplifier is working. Now this is without the load. Let's say that we stopped the simulation and we connected our variable resistor here, and let's say that we put here a voltage source, a variable resistor value of 47 kilo ohms. So what will happen with our uh, output voltage? So we have a 47 kilo ohms load resistor, and the input is still the same. It's still zero point 0.8 volts peak to peak voltage. And let's see what will happen. As you can see, the resistance 47 kilo ohms made the peak to peak voltage from 6.8 to become lower at 3.8192. So it means that the effect of the load resistance to the gain, before, without the load resistance, we have an output voltage of 6.78 or 6.8, and now it becomes 3.8. Now let's try to lower the value of our resistance. Let's make it, let's say, 18 kilo ohms. So the effect is that the peak to peak voltage output becomes much lower also. So we can say that the output voltage becomes lower if the resistance also is lower. And if the resistance is higher, like here, we have an 18 kilo ohm resistance in the load, and the voltage output is just 2 volts. But when we increase the resistance in the load to 47 kilo ohms, the output voltage becomes 3.819. And of course, if you remove the load resistance in the load, then the output voltage is at its maximum of 6.87 volts. And considering that the capacitor in the emitter is not yet connected. Now let's try to connect the capacitor across the resistor which is connected in the emitter, or the RE or R4, parallel to the capacitor CE, and let's see what's the effect. So when we connected the capacitor CE across the R4, which is connected to the emitter of the transistor, the output voltage or the peak to peak output voltage becomes 11.425 volts. So this is a much greater increase compared with uh, the one where we did not use the capacitor across R4. So the capacitor CE in effect helps in increasing the output voltage of the amplifier. Now let's try to change the resistance across the load resistance here. So let's connect the load resistance, and let's say we have 47 kilo ohms, same as before, but this time we have the capacitor in parallel to the R4 or the RE. So let's see the result. So the voltage output is still high at 9.609 or 9.6 volts. Therefore, it will be better if we connect a capacitor across R4 because the VPP output will be larger than not using this capacitor. So we can say that the CE really helps in increasing the output voltage of our amplifier. Now let's try it with 18 kilo ohms. So the VPP in the output side becomes 7.8867 volts. So still in comparison with the other circuit where we did not connect the CE, this is still higher. So this is the gain at different loads of a basic common emitter amplifier. Now, if we will be experimenting on the different values of the load resistor connected at the output side without the CE, and with the CE, we can create a table that will clearly represent the effects of varying the RL without the CE and with the CE. So let's see some results. So let's see again the gain at different loads of a basic common emitter amplifier, and you will see here that the gain at different loads of a basic common emitter amplifier, as we have done before, the signal generator here or the voltage input is given, and these are the values that we have done or we have used. And this is an example of a circuit that shows you the effect of doing the circuit connections. And this is the result of a table without the CE. And as you can see here, when the RL is not connected, the input voltage peak to peak will be 798 millivolts all throughout the variation of the RL, and the output voltage peak to peak, as you can see here, starts from 6.8699 volts. Then it becomes lower to 3.8192 volts when we connected the RL of 37 kilo ohms. And furthermore, if you connected an 18 kilo ohms on the RL, the output voltage peak to peak will become 2.1152. And lastly, when we have 4.7 kilo ohms, it becomes around 0.69 volts. Now, this clearly represents that the RL's effect on the amplifier is that the higher the RL, the higher will be our output peak to peak voltage. And if you will be calculating the gain, of course, the gain is calculated by dividing the output voltage by the input voltage. So that will be 6.887 volts divided by 0.798 volts, and we will have an answer of 8.6. This will be our gain. And as you can see, the gain in a similar fashion becomes lower compared with the output voltage. So if the output voltage is decreasing, of course, the gain will also be, or the voltage gain will also be decreasing. Now, when we have connected the CE across the R4 and we varied again the RL from no load 47 kilo ohms, 18 kilo ohms, and 4.7 kilo ohms, the uh, voltage output peak to peak becomes 11.425, 9.6, 7.8, 88 or 89, and 4.51 volts. As you can see, compared with the one without the CE, there's a significant increase from 6.86, it becomes 11.4. From 3.8, it becomes 9.6. From 2.1 volts, it becomes 7.9. And from 0.694 volts, it becomes 4.5 volts. Accordingly, the voltage gain also increased compared with the without the CE. So from a gain of 8.6, it now becomes 14.3, and so on. So it clearly shows that the usage of the CE across the resistor connected on the emitter will definitely increase the gain. So there you have it. This is the result of uh, the gain at different loads of a basic common emitter amplifier. I hope you understood what I have shown you, and please subscribe, share, and like this video towards the road or our road for 1,000 subscribers. Thank you so much.